Today we're going to talk about taking the derivative using what we call shortcut rules. This is usually a fan favorite because yesterday's lesson on using the limit-based definition was probably pretty taxing, but definitely necessary because it did apply some of the things we know about limits. So here are the four basic derivative rules that we're going to use today. And the first one is that if the function is a constant function or it's equal to a number, the derivative will always be 0. And then we have the power rule, which says we're going to take the power, put it in front, and then reduce that power by 1. Power rule with a constant, we're going to multiply the power by the constant in front and reduce the power by 1. And the sum and difference means if we have a polynomial, we can differentiate term to term. And then we're going to end today with an application of the derivative. So when we start, we're going to look at this first one. It says f of x equals 7. That's a constant function. So f prime of x, which is my derivative, is 0. No work required. So I'm sure you're probably applauding me quite nicely. I would have loved to have seen that in person. Okay, here we go. So power rule here, f prime of x. We're going to bring the 3 in front. We're going to write down the x, and we're going to reduce that power. 3 minus 1 is 2, and that is your derivative. And then we could go and find the tangent slope at any point on our curve. Here in 3, I recommend we get rid of that radical and use a fractional exponent of a half. And now when we go to find our derivative, it's f prime of x. And then we're going to multiply the 2 by a half. So 2 times 1/2, write down the x. And then we're going to reduce our power on the top, 1/2 minus 1. So my derivative is going to be x to the negative 1/2. Honestly, I'm not bothered by the negative exponents. You can leave it like that. You can also write it 1 over x to the 1/2. I'll be really flexible there, and really negatives and the exponent aren't really going to bother us too much anymore. Okay, so moving forward to the next one, we're looking at 4/5 x squared. So there's a constant in front, so f prime of x. We are going to take 4/5, we're going to multiply it by 2, we're going to write down the x and decrease our power, and then f prime of x equals 8/5 x. So again, the work is whatever you need to do to show that you understand. You can kind of, once you get good at it, which as you progress to calculus, you're going to be taking derivatives all the time, and this will just become second nature to you. Okay, so in this next one, rewrite with the negative exponent here so we can apply the power rule. And then again, f prime of x in that notation. We're going to take negative 3 times 5/2, which is negative 15/2, x to the negative 4. Be careful on the minus 1 there with your baby integer rules. And again, you can leave the answer in that format. You can also write it negative 15. The 2 goes on the bottom, as does the x to the 4th. So that really is up to you. Okay, here's an example of the polynomial. Now we're going to put the power rule in place twice. So for the x cubed, we move the 3 in front, we copy the x, we lower the exponent. In the next one, we multiply that understood power of 1 times a 4, and when we reduce the power, we get x to the 0, which is a 1, and then the plus 5, the derivative of any constant is a number. Now just for a minute, revert back to yesterday's lesson. That would have been quite the task using the limit-based definition. Next year in calculus, though, you'll see multiple forms of that. I just wanted to show you a little bit about what was going on. Okay, here's another polynomial. So again, we're going to employ the power rule here. The coefficient here is a negative 1/2 times 4, which is negative 2. X, drop the power by 1, plus 3 times 3, 27. drop the power by 1, x squared, drop the x here, minus 2. So that's kind of the rundown in the rules, much simpler, and that's what you'll be doing the vast majority of the time. Again, we have to emphasize the limit-based definition because of where we were heading. Okay, now we're going to do the equation of the tangent line, much easier. The first thing I would do is rewrite my function as x minus 1 to the 1/2. And so my derivative, using power rule, 1/2 x minus 1 to the negative 1/2. And then I would rewrite this just because we are going to plug into it, and it'll be a little bit easier to see. So 1 over 2 times x minus 1 to the 1/2. And now we're going to plug in. So we want the equation at 5. So I need to find the slope. So here comes the slope at 5. 1 over 2 times, and that's where I'm going to plug in my 5. Okay, so 1 over 2, 5 minus 1 to the 1/2. So that looks like that's going to be 1/4. So there's our slope. And then we're going to find f of 5, which means that goes into the original function. So the square root of 5 minus 1, that's a 4, that's a 2. So now that means my point where I'm finding the tangent is 5, 2. And now we're going to use our point slope. So y minus 2 equals slope 1/4 x minus 5. And then we'll just solve this for y. So y minus 2 equals 1/4 x minus 5/4. And then we will add a 2 to both sides, and the equation of my tangent line, 1/4 x plus 3/4. And there is our equation of our tangent line. Okay, we're going to do one quick application here. We're going to talk about position as we move along. It's a straight line. It's called rectilinear motion. It could also be moving along a curve. And the velocity is s prime of t, which means the velocity is the rate of change in the position function. And so we're going to take the derivative to get that. So just a couple things that go together. And the first thing it says is that we're thrown straight down from the top of a 222 building. We're going to build our position function based on what we see here. So we're going to use our model. So s of t, we're going to take 1/2 times the acceleration due to gravity, which since we're in feet, negative 32 feet per second, t squared, plus the initial velocity, and ours was negative, so negative 22t, and the initial position height, which is 220. And then if I clean up my function, I get negative 16 t squared minus 22t plus 220. So there's our position function. So when we want the velocity, we're going to take the derivative of the position function. So that would be negative 32t minus 22, and I did that using the power rule. And we want to know the velocity after 3 seconds. So that means I'm going to plug 3 into the velocity function. So 32 times 3 minus 22. And that's going to give me a negative 118 feet per second. And remember that the velocity function is the rate of change. So let's see if I write that up here. The velocity function is the rate of change, and you know that, and this is a big buzzword in in calc is that the rate of change means slope. So we're talking about the slope of the position. And so that's why we take the derivative. So that's why our velocity function is the derivative of the position. Okay, now let's work, this first part was pretty simple. Now let's look at the second part. So in the second part, they want to know the velocity after falling 108 feet. So I'm going to put a little asterisk there. You need to find the time it took to fall 108 feet. And then we're going to plug that into the velocity function. So the first thing is our initial height was 220, and we fell 108 feet. So our height now is 112 feet. And this again is the height after falling 108 feet. Okay, that's what's left. Now we're going to plug it into, because this is about position. So we're going to go to our original position function. So negative 16t squared minus 22t plus 220. That's our original. And right now, my height is 112. So negative 16t squared minus 22t plus 108 equals 0. And now we are in in a quadratic. We can take out a GCF. I'm also going to pull a negative here. 8t squared plus 11t minus 54. Remember, we're talking about time too, so we have to be realistic about our restriction here. Negative 8. Oh man, boy. Okay, hold on, time out. Back up. Let's take this line out. I'm way ahead of myself. So what I'm going to pull out here, I'm going to pull the negative 2. Sorry about that. You're probably looking at it if you're watching this video going, good Lord, what is her deal? Okay, let's try it again. 8t squared plus 11t minus 54. And then we're equals 0. And now we're going to factor. Boy, oh boy, my goodness. Okay, so we get an 8t and an 8, 27, and a 2, and a plus, and a minus. And remember, a negative time can't factor in. That negative 2 in front is not meaning anything, so our time is 2. So it took 2 seconds to fall 108 feet. And now we would like to know the velocity, which now at that time, which is v of 2. So we go back to our derivative, 32 times 2 minus 22. That's negative 86 feet per second. So just another small, you'll see lots of applications for the derivative, but I just wanted to show you a quick one to kind of expose you to the ways that we can apply that.